Power is a quantity like velocity or acceleration, which represents a rate of change of some quantity. For example, in our first unit of study on kinematics, we learned that velocity is a rate of change of position. And we can write that mathematically. An average velocity, symbolized with a V with a bar over the top of it, is equal to a change in position divided by the corresponding change in time. That's how we define average velocity, right? It's a rate, the change in position divided by the change in time. Instantaneous velocity is equal to, well, really the same quantity in the limiting case where the time interval gets less and less and less and ultimately approaches zero. Or in that case, we say velocity then is equal to the derivative of position with respect to time. Okay, well, in a similar vein, power is also a rate of change. It's not the rate of change of an object's position, it's the rate of change of an object's energy. Although we could amend that and note that change of energy is a quantity we know of. An object's change in energy is equal to work. So average power can be defined as an equation. It's equal to a change in energy divided by the corresponding time, or we can say it's equal to some amount of work divided by time. Instantaneous power is then equal to the amount of work divided by time in the limiting case where the time interval approaches zero. Or in other words, power is equal to the derivative of work with respect to time. Now let's take a closer look at this. Let's say an object is being pushed by some applied force, but that force might vary with time. Then to find the work done, we divide the displacement up into a bunch of little incremental bits, each one with a value of ds. So we can say that a little bit of work is done in each one of these intervals. And that little bit of work is the instantaneous value of force multiplied by that incremental displacement. So power can be expressed as F dot ds over dt. Hopefully you see we've just rewritten this expression, right? We've replaced a little bit of work with this quantity F dot ds. So if we rearrange this slightly, we can say power is equal to force dot product with ds dt, but hopefully you recognize what ds dt represents. That's velocity. So instantaneous power is equal to the dot product of the instantaneous force and the instantaneous velocity. So we have two working equations for power. Average and instantaneous. Average power is some large amount of work done over a relatively large time interval. Instantaneous power is the rate at which work is done, which in turn is equivalent to the vector dot product of instantaneous force with instantaneous velocity. Now let's look at the units for power. If it's work divided by time, then the units are joules per second. And there's a special name for a joule per second. 1 joule per second is known as 1 watt. 1,000 joules per second then would be the same thing as 1 kilowatt. Some people get a little mixed up on these units. There's an unfortunate side effect of honoring former physicists by giving a name, by naming units in honor of people like Newton, right? The unit for force is the Newton. The joule is named after James Prescott Joule. The watt, the Pascal, so on. There are so many units that are named to honor those who came before us. The problem is you lose sight of the definition of the quantity. Power is a rate, and there's nothing about watts that would give you any indication that it involves rate. Now, if you were told a certain number of joules per second, then you immediately understand that there's a rate involved. Whenever you hear per second, you know it's a quantity that represents some kind of rate. If you hear watts, you lose sense of that definition. For example, San Onofre, I believe they call it SONGS, the San Onofre Nuclear Generating Station. So it's no longer online and producing electricity, but a few years ago it was, and it was converting nuclear energy into thermal energy, which was harnessed by way of a turbine, which really a coil of wire spinning in the presence of a magnet, which generated electrical current. And the amount of electrical power that was being sent out into the grid was about 1.2 gigawatts. In other words, 1.2 times 10 to the 9th watts, or 1.2 billion watts. That was the power output. Now, some people hear that number are impressed, right, just because they recognize it's a large number. Unfortunately, a common response that I would get when I tell people that value is say, oh, yes, 1.2 billion watts, that's a lot. 1.2 billion watts per what? Per day? Per week? Now, if somebody asks that, certainly they don't understand what a watt is all about. The per is already built in. When I say 1.2 billion watts, what I'm really saying is 1.2 billion joules per second. So you can never ask how many watts per what amount of time. Time is already built in to the measurement of watts. So be careful when expressing quantities in watts. It might be of benefit as an introduction to express power as a number of joules per second. But certainly keep in mind that 1 joule per second is commonly referred to as a watt. Thanks for watching.